three resistors, appropriately labeled R1, R2, and R3. R2 and R3, right here, are connected in parallel. And R1 makes up the series. R2 and R3, once again, form the parallel branches. And R1 is the series component. Now, what is it that makes this a series parallel circuit? Could it be the fact that it has a power source, or the fact that it has conductors, or the fact that it has a load? No, these are required for any circuit. The main characteristics of this circuit are that in part of it, all of the current is passing through the same component, right here. And in other parts of the circuit, the current divides and has more than one path. Now, I'll draw the flow of this current on this diagram. Now, this shows that all has to pass through R1. Now, let's label R1 as the series component. The current through R2 and R3, of course, be less than total. This then tells you the basic requirement for a series parallel circuit. First, it must have a series component, right here. It could have more than one series component, but it must have at least one. Secondly, it must have two or more parallel components. All right, let's take another circuit for an example. How about this one? All right, is it a series, a parallel, or is it a series parallel circuit? Well, if you said series, you're right. There's no parallel to it. Every single resistor right here is going to carry total current, is it not? All right, we're going to make a little change. And I warn you to watch out, because this could be just a little bit tricky. All right? Now, what kind of a circuit is it? If you said parallel, you're right. Now, if you were a bit confused, I suppose here is where you jump the track. Remember, the four original resistors, 1, 2, 3, and 4, are in series with each other. And that could fool you into thinking that this is a series parallel circuit. But none of the four resistors is carrying total current. And of course, this new resistor right here is certainly not carrying total current. So this circuit does not meet the qualifications. It, of course, lacks the series component. All right? Now, it's easy enough to turn this into a series parallel circuit. It's already parallel. So all I have to do is to add a series resistor in a place where it will carry total current, right here. Now, it's a what? Of course, it's a series parallel circuit. As you can see, it's going to be easy to get fooled on series parallel circuits if you try to go by appearances only. Well, the real test of a series parallel circuit, and the surest way to decide if it is series parallel, is by considering current. Now, if it has a series component that is carrying total current, that's total current, and two or more, that's two or more parallel components carrying partial current. Then it is series parallel, no matter what it looks like. Now, to be sure that you have the idea, will you complete this one for number 1 on your sheet? Well, there are many ways you could have said it, just so you have this idea. Now let's see if you can draw this type of series parallel circuit for number 2 on your response sheet. You should have drawn a circuit like this one, or its equivalent. There are several ways you could have done it. If you have a series component and 2 or more parallel components, you're okay. In series parallel circuits, we have the same old problems. There will be cases where you'll want to find voltage, current, and resistance at various points in the circuit. What you've already learned about series circuits is still true, and what you've learned about parallel circuits still applies. The only problem in series parallel circuits is that you have to sort of mentally flip back and forth, depending on which part of the circuit that you're considering. For an example, let's consider this circuit and solve for a combined resistance of R2 and R3 by applying Ohm's law. First, let's find the voltage drop across R1. At this point, we can, of course, ignore R2 and R3, which is the parallel portion of the circuit. We simply treat R1 as a series resistor, which it is. Now, we can do this by using this form of Ohm's law. All right, E1 is equal to I sub T times R1. By substituting the known quantities of I and R, we have then E1 is equal to 5 times 10, or 5 times 10 is 50, which is, of course, 50 volts. All right, let's put it up here. E1 then is equal to 50 volts. Therefore, we can say that the voltage drop across R1 is equal to 50 volts. Now, let's find the voltage drop across each parallel branch. We know now that the drop across R1 and the drop across the parallel branches, that's R1 and the parallel branches, must add up to the battery voltage. So all we have to do is to subtract the voltage drop across R1 from the applied voltage. Very simple. Minus, of course, 50. And we have what? 60 volts. 50 subtracted from 110 is 60. We can then say the voltage drop across each parallel branch is equal to 60 volts. Let's put that down. As you recall, both R2 and R3 will have the same drop since they are in parallel. Remember that. Now, you try and solve for R2. Do it one step at a time. This will be number 3 on your sheet. You know the voltage across R2, and you know the current through it. So what form of Ohm's law do you need? Write it down, and I'll wait. Okay? You should have picked the form R equals E divided by I. In this case, it would be R2 is equal to E2 over I2. Now, substitute the actual circuit values into the formula and solve for R2. This will be number 3 on your response sheet. You should have substituted 60 for E2 and 2 for I2. 60 divided by 2 is equal then to 30 ohms. R2, 30 ohms. Now, will you solve for R3? I'll wait. Well, you should have answered 20 ohms. Now, let's find the combined ohmic value of R2 and R3. We can ignore R1. We've learned all we need from it. R2 and R3 are in parallel. so we could use the reciprocal formula. However, since we're only dealing with two resistors, it'll be easier to use the product over the sum formula. And I know you recall it's this. R2 and R3 equals R2 times R3 over R2 plus R3. Now, by substituting the two known values of R2 and R3, we have R2 and R3, thereby equal to the value of R2, 30 times 20 over 30 plus 20. Now, let's multiply 30 by 20. 600. And 30 and 20 equals 50. Now we have 600 divided by 50, which is, of course, equal to 12 ohms. So the combined ohmic value of R2 and 3 is therefore 12 ohms. All right, let's see if you now have the idea. In space number 4 on your response sheet, solve